but he is also
Thank you so much. So it's a great pleasure to be here, and I know that we have an online audience in addition to an audience in person. I like to give talks in which it's a little bit interactive. People are willing and hopefully able to ask questions as we go. For those of you online, I may or may not be able to see your questions until we get to the end. So please accept my apologies in advance. If I miss your question, I will capture them and I'll go for online questions first when I finish the talk. It's a pleasure to be back in Illinois at Urbana-Champaign. I think I was last here 5 years ago, where I was talking about the physics of acceleration sensing and things we can do with it. Things have moved on quite a bit since this. It's been a very tumultuous 5 years, or adventurous, perhaps. As was mentioned, I am a fellow at the Joint Quantum Institute, which is a collaboration between the University of Maryland and NIST in Gaithersburg, Maryland. And I'm also now the chief science officer of a company called Riverlane, which builds embedded systems for quantum computing devices. Today, I'm going to talk about a journey from science towards engineering. And I've given this a somewhat provocative title of the birth of quantum engineering. But it's really meant to represent the fact that the field of quantum mechanics, quantum information, and quantum technologies are converging towards not can we do it, but what are we doing? And what shall we do? And this picture is from my colleague at NIST, Jun Ye, and his laboratory where they build the world's best atomic clocks, which are, of course, one of the preeminent examples of deployed quantum technologies, which we use and take advantage of every day, primarily through the global positioning system, but through other systems as well. So I know that this is a somewhat diverse group, and I appreciate that I will go slow and then fast and then slow again. So again, feel free to raise your arms, get your questions and ideas out there as we chat. I do want to start though by just saying a core point about quantum mechanics is that if you think about quantum theory and its application as a technology, it doesn't actually do much by itself. It's what you might call a base technology. So for me, the canonical example of that is the atomic clock, which I just mentioned. In the atomic clock, you use a two-level system, a quantum bit, typically encoded in levels of an atom. You prepare this quantum bit in an initial state. You tip it up onto a corner of this thing called the Bloch sphere to let it process freely under its own internal dynamics. Those internal dynamics are hopefully given by nature, since every atom is identical, as seen in the examples of Bose-Einstein condensation and other phenomena. They should all have the same precession rate, independent really of where you are. And so if you can check that precession with a local oscillator, you can then compare by measuring at the end of whether you got up or down, what you expected, so the thing spins about. You compare your local oscillator to the spinning of this atom, and that makes a clock. The local oscillator is a sinusoidal signal, which is your actual clock signal, and you're comparing that sinusoid to the internal rotations of the atom. The first realization of this was actually done at the National Bureau of Standards, which used to be NIST before the Reagan administration. And at MBS, this is actually an ammonia clock that's in the museum they have there. It uses transitions in an ammonia molecule. It was only accurate to part 10 to the 18, 10 to the 11. And then what you can do with this, though, is, and this was realized through a series of experiments and technology demonstrations and engineering, is take advantage of First of all, the idea that you have good timekeeping regardless of where you are, because atoms are the same everywhere. Take advantage of the speed of light being nearly constant. I mean, it's constant, but of course, in an atmosphere, it changes a little bit. In order to convert between time and distance. And if you put up a constellation of objects, the intersection of multiple four spheres, so time and space distance locations, of these objects tells you exactly where you are on Earth. And thus you have two physical concepts, or three really. Atoms are all the same, that you can probe their properties, and that light travels at the speed of light in order to build a technology, which is the global positioning system. So the base of the technology is quantum mechanics, but there's a huge amount that goes into making this thing work. It wouldn't happen without quantum mechanics, but it certainly won't happen just because of quantum mechanics. So you have this base technology, you can build things on top of it. Now, the consequences of these choices are hard to predict. Like, you wouldn't have predicted when you invented the atomic clock in 1949 that in 2009 the taxi market would have been transformed by atomic clocks. It's not the only thing that caused the transformation of the taxi market, right? But the advent of Uber, Lyft, and other ride sharing was driven by the technology that was enabled. If you own the base technology, you own the productivity gains, you own the benefits for your citizens. And this is a core point behind why the US has the National Quantum Initiative. Now, this is another atomic clock from NIST in 2009, where this object here, which is human-sized, has been replaced by this object here, which is dime-sized. The accuracy has gone up from 1 part in 10 to the 11 to 1 part in 10 to the 15. This is a so-called chip-scale atomic clock, and now you can actually buy chip-scale atomic clocks for several $100s. So there's engineering that goes from here to here, there's science that goes from here to here, and there's technology enabled on top of it. That sort of dialogue is, for me, the key thing to remember when we talk about quantum technology. We're talking about engineering quantum systems. So what are our quantum modalities? Of course, the one I've just talked quite a bit about is quantum sensors and quantum sensing. And I'm going to spend quite a bit of the latter half of the talk diving into applications of quantum sensing. But you have two different modalities, or two different ways of thinking about quantum sensing. One is accuracy via physical law. We just had an example of that in the course of atomic clocks and the global positioning system. But there are other concepts, like electrons are quantized. So they have a fixed charge, and this is used to calibrate electrical currents and voltages through quantum Hall standards. And together, we've actually been able to convert this with this in order to make what's called a Watt balance, or a Kibble balance, which is an object that converts fundamental constants into mass, which is how we now realize the kilogram at NIST. Overall, you should understand this accuracy via physical law has been codified in what's called the quantum SI. So all the nations that agree on the Metrology Treaty, first signed back in Paris in 1888. That Metrology Treaty is still today how we do weights and measures across the globe. And now every single element of how we do weights and measures is tied to a quantum standard. So there's no more artifacts, there's no more piece of platinum sitting in a vacuum jar. There's 20 of them around the world. That's now out. We now can realize these standards anywhere in the world using quantum technologies. But the other point is that there's new modalities of measurement. That is to say that you can measure where you just couldn't measure before. So for example, one great example is LIGO. For those of you familiar with the laser interferometer that's used for gravitational observations, in order to see very distant black hole inspirals, you need to go below what's called the standard quantum limit. Go below the back action limit set by quantum mechanics. It's not the Heisenberg limit, it's well before that, but it's the single particle limit. And LIGO now does that routinely using squeeze light. So that's an example of something you couldn't have done before, but with quantum technologies, particularly quantum 2.0, using entanglement, squeezing, things of this nature, you can open up an area you couldn't see before. The other more common one is magnetic resonance imaging, right, which I imagine I'm not going to say the majority of people in this room, because there's a lot of young faces, but for those of us who are a little bit older, you've probably had at least one MRI in your life. And that's actually a key technology. So I just want to mention that both of these really matter, and there's a lot of developments on both directions. The second area of great interest is quantum computing. And this also has two different sort of themes, one of which is the theme of really first promulgated by Phil Anderson and then later amplified by Feynman. And there's a great Russian theorist whose name is eluding me, who no one knew about it until about 15 years ago, who also was talking about it. But anyway, the key point is that the best thing for simulating a quantum system is another quantum system. And I want you to think about a different analogy, which is fluid dynamics. So as you may be aware, fluid dynamics is a challenging numerical problem. The Navier-Stokes equation, in fact, and certain variations, is NP hard to solve. There's a great proof by Terry Tao about that. And so what do we do when we want to actually build a car or an airplane? We do a combination of things. We use digital simulation on computers, and we combine it with controlled analog simulation, like in this wind tunnel here. So today's quantum simulators are controlled analog emulators or simulators of quantum dynamics of other systems, which allow us to test our pen and paper intuition and our regular digital computer intuition. In the future, we can go beyond just simulating Schrodinger's equation and hopefully go into a domain where we're building direct understanding using quantum computers all the way, rather than just these sort of nascent quantum simulators, which do an imperfect job of emulating. We have to make a lot of projections about what really is happening under the hood. But then beyond that is sort of full-scale quantum computing, which is in the error-corrected regime, where you use quantum error correction, and we'll talk about that towards the end, and use that to get to a regime where you can make an arbitrary large computation on arbitrary data. And these programmable quantum machines are really moving from the lab into systems engineering. There's a variety of different approaches, some of which are the atomic qubits, superconductor qubits, semiconductor qubits, even topological qubits, all very interesting, but not the focus of today's talk. What I'm more focused on here is how you actually do the systems engineering, because this is, after all, about the birth of engineering. And then finally, and I won't go into much detail, once you have quantum computers, and you've got well understood quantum sensors, you want to hook them together. And this is quantum networking. And quantum networking has both quantum communication components, some of which is like quantum key distribution, today deployed technology, but more future looking is entangling sensors at distance to enable better sensing. But it's also quantum cloud computing. And there's been some really interesting advances in using quantum computers that are entangled together in order to do larger computations, and also interactive and cryptographic protocols that there is no classical analog for. So I believe I've made a case to you that these are really interesting things to look into, to dig into, to do better at. I believed this so firmly, I ended up accepting a position at the White House back in 2017 to lead an effort across the US government to make a deeper investment in these technologies. And this is a summit that we hosted in 2018 before the National Quantum Initiative Act was signed, essentially laying out with the academic and industrial communities the policy framework that the US was going to take going forward. I had the pleasure of moderating this conversation with the various heads of our agencies. And the US strategy is we put together in that time is what guides the current effort. It has a number of key things, but the first thing I want to lay right up at the top here is focus on a science-first approach. So this is a recognition across the federal agencies and the whole US R&D ecosystem that in 2018, quantum systems weren't ready to just be developed as an engineering project. But there were substantial science questions that have to be answered before you could really engineer. And when I talk about the birth of quantum engineering, I'm talking about the eventual transition from this science-first approach to a society-driven approach in which it's not just about doing better science, but it's also about taking that science and making impact for our citizens. And that's what engineering is really about. Making something practical, reliable, usable, and hopefully not too dangerous. There's other things here which are also very dear to me, but I won't talk about in detail today, about building a quantum workforce, having good industrial engagement and public-private partnerships, and I'm learning that very viscerally in the course of working at Riverlane this year and more. Getting the infrastructure and support around the opportunities, driving our growth and maintaining our security at the same time, and developing international collaboration and cooperation. If you want to read more about these things, please go to quantum.gov, and all the latest stuff is up there. I encourage you, if you're interested in getting more involved, please do so. There's a lot of opportunities. But let's talk now about this engineering part. So my point here is that the engineering need in quantum computing in particular, but also quantum systems more generally, is growing. So here is here's John Martinez's quantum computer from 2013. This is about 6 inches, for those of us who use an inch, so by the way, is 2.54 centimeters, just to be clear. So 6 inches across, a chip here, lots of wiring. This is the 120 some qubit machine from IBM with all its wiring here in 2021. So from here to here is a substantial increase in complexity. And now you're looking at, well, I made one thing that worked, let me make 100 of them that worked. Let me integrate this 100 things that worked with these 100 things that worked, with that 100 things that worked, with that chip with 100 things on it that work. That's systems engineering. Each individual component being able to be reproduced, be integrated together. And that's really challenging. Because you can normally look at, can it work? You ask, am I within my tolerances for this working, so that they all work? Defective parts are just not, you can't handle it. You have to have enough yield across the whole device to make the thing work. And that means moving a framework of thinking from, it will work this one time with duct tape, bubble gum, literal dental floss, and sweat and hard tears from graduate students, to it'll work every time. What I love about getting into this engineering space is that every great experiment is driven by the edge of what's possible. So as you go towards building larger quantum computers, a huge new swath of science opportunities are going to emerge. So let's talk about this engineering side in the context of an applied problem for quantum sensors. And this is an effort I've been involved in the last 5 years or so, which is using quantum sensors to try and find dark matter. So who here has seen dark matter? What is it? Okay. An artist rendition. Well, we'll have more artist rendition of dark matter today as well. So the short answer is that we have a lot of evidence out there that galaxies have more mass in them than we can see in the combination of their dust, gas, and stars. A lot more mass. This extra mass is called dark matter. We know that it's probably at smaller scales than 1,000 kiloparsecs, but that's all we know about it. Oh, and it gravitates. Okay, so what is it? Well, we don't know. Particle physicists have been really intrigued at the possibility that dark matter could be particulate in nature, so not like small black holes or little planetoids somewhere, but actually fundamental particles. And so they've been looking for it. Here is a logarithmic scale. It's like the universe scale. Up here you have 100 Planck masses. So that is just under a gram, or sorry, just under a milligram in terms of energy. So the energy stored in a milligram of material. And then over here you have 10 to the minus 22 electron volts, which is roughly a photon whose frequency is like some billions of years, or its period is some billions of years. So it's a wide range. possibilities, if it's particulate. One of the things that we do know from observations is that the density of dark matter is, it's roughly speaking, about 1 proton worth of mass per cubic centimeter or so. So that's not a lot of mass. It's very, very less dense than the vacuum of space. But because it spreads so widely, it ends up being larger. There's some halo around galaxies, we think. It ends up being a big effect. And what we're going to zoom in on is the question, well, can we measure something about it using quantum sensors? And here is an example put together by one of my colleagues in the UK of the previous Prime Minister, who liked to hit a gong, it turns out. So that I have a gong here represented by a mass, spherical mass for a physicist of me. And here is a bit of artist rendition of dark matter. So one thing we know about dark matter is it gravitates. And if you go back to your introductory mechanics, you may remember that you get these, when two things go by each other and they're gravitating, you will actually have a change in their trajectories, right? So there it goes by. And this bend here has shifted the momentum of that particle. Conservation of momentum tells you that momentum went into this particle's motion this way. So when a dark matter particle goes by a mass, it will cause an impulse, a force over time. And in principle, that mass will ring for some period of time, based on the fact that it just had an impulse applied to it. What's amazing is that with quantum technologies, with what we can do for measuring stuff, we can, in principle, start to build a detector that's sensitive to the gravitation of dark matter particles. I will mention that the same sensor I'm going to talk about today also can be used to extract dark matter particles that have a standard model cross-section, so that interact with matter beyond just gravitation. And there's a nice result from some of my collaborators on that from 2 years ago, and where they're trying to make levitated spheres to measure the ultralight dark matter. But I'm going to focus on dark matter that's heavy enough that you can, in principle, see this impulse. So this is dark matter that's in the Planck mass regime. So individual sort of fundamental-ish particles whose mass is about 21 micrograms to about 1 milligram. And that turns out to be a natural scale if you're a quantum gravity theorist, because what we don't know about the standard model is what happens when you get to the Planck mass. That's where gravity should be a very strong effect. And so Planck mass particles have been proposed by a number of theorists. No one knows what they would be, but there's a reason to believe that they might be there. I will mention this is going to be very hard. I just want to get that right off the bat here. So if you ask, what's the change in velocity of this particle? I'm doing change in velocity because gravity produces a force proportional to mass. So the impulse is momentum times velocity, but the change in velocity is independent of the mass of this object. So it's a very convenient measure. And you can figure it out pretty quickly by the impact parameter, so how far away this particle, this vertical line is, this horizontal line is from the center of the mass of the particle, the velocity of the dark matter, the mass of the dark matter, and Newton's constant, big G. Spoiler alert, big G is small. I don't know why they call it big G. So this impact parameter is limited by the radius of the object, and what you find is that the change in velocity is about 10 to the minus 21 meters per second, times the mass of dark matter compared to a Planck mass, times a centimeter over the radius of the object. So it's a pretty small change in velocity. And now we want to see, can we see it? Go ahead.
What about
I did mention it before. So the dark matter density is about 1 proton mass per cubic centimeter. So for these particles, at Planck mass, if you build a 10 meter by 10 meter detector, you expect an annual flux of dark matter particles of about 10,000. So it's not a huge flux. Of those, you're not going to detect most of them, actually. If you go down to 1,000 Planck masses, then you only get 10. So that's why we can't go more than about 1,000 Planck masses, because we just don't get enough flux in a year to try and measure something. But yeah, there's not that much of it. Okay, so how do we go about measuring this stuff? Well, I want to remind you of what's called the standard quantum limit. Okay, so the proviso about the standard quantum limit. It's not standard, it's not quantum, and it's not a limit. Good. But if you make a simple argument about a single particle, you could say, well, let me see what happens. If I take a particle and I measure its position, the measurement with some imprecision delta x, that measurement will lead to an uncertainty in momentum, which leads to a later uncertainty in position. So vertical axis here is momentum, horizontal axis is position. And if you know if I have some momentum and I wait for a free particle to evolve, momentum going leftward makes the particle go this way, and momentum going rightward makes the particle go this way. And so eventually a particle that was very tight becomes very spread out. So the later uncertainty in position is set by the time in between measurements divided by the mass times delta x. If you try and optimize this, you get a length scale, which is called the standard quantum limit for position sensing, which tells you how well you can average out measure the position of an object over time. However, that was not the button I wanted to press. There we go. However, if you do this once, there you go, you can also estimate, by the way, the velocity by looking at the difference of these two positions and dividing by time. That's a numerical derivative of velocity. Remember, for dark matter, we want to see the change in velocity, right? So what we really want to measure is velocity. And you look at this standard quantum limit for velocity, and it's like the standard quantum limit for position. You end up looking at square root of 2 because there's two measurements. And then you divide by tau. So overall, the longer the time between measurements and the higher the mass, the better your velocity standard quantum limit is. Which means that for like this very challenging measurement of delta V we mentioned, we're going to want larger masses, and we're going to want long times in between measurements. So you want really good, very coherent masses in order to make this type of measurement work. So what happens when you go to long integration times? Well, first of all, there's this velocity standard quantum limit, so measurement, it puts a limit on how well you can do. You want to go to long times, but unfortunately, you know, if you have a mass and it has some friction, so there's momentum is the friction term, there's going to be a corresponding thermal force. This is the fluctuation dissipation theorem requires this to exist, and this thermal force produces a velocity noise that goes as the square root of the time between measurements. So on the one hand, longer measurements are good because you can really push the quantum noise down, but eventually the thermal noise comes and kills you. It is worth mentioning that there's this thing called the quantum coherent limit, in which the temperatures, the frequency scale associated with temperature is much less than the Q frequency product of your mechanical system, which has now been reliably and routinely observed in laboratories around the world. So the fact that we may not be thermally limited is now almost taken for granted. And that's a great tour de force of the electromechanics and optomechanics communities, some of whom are in the audience here. But what happens when you do this? Well, my animations are all backwards, but that's fine. So remember, there's the energy, the length, the velocity scale I wanted to know. Here's my sort of SQL, and here's that thermal limit for some of the best masses that we can conceive of right now. So actually, we'd like to be here, but because we're going to high mass, we end up being limited more by the thermal term here, and that's not so great. So this is using 10 millikelvin temperatures, high density material spheres, and dark matter velocity of 200 kilometers per second, which is the best theoretical estimate we have for how fast it's going to be going by the Earth. You can try and optimize this to find the best integration time possible, and you end up coming up with about 5 times 10 to the minus 14 times a variety of relatively reasonable numbers here. So remember, 22 is what you're targeting, 14 is what you get. Obviously, you can improve the temperature, go down to dilution refrigerator temperatures. This is a squeezing parameter, so if you use squeeze light to do this measurement, you can do a bit better by how much squeezing you have. Bigger masses will help. longer coherence times for mechanics will help. But it's hard. So that's the same thing I just mentioned. Okay, so how can you go to lower heating rates? Well, if you decouple the mass from a support, you get rid of that friction term, which gets rid of that thermal heating. What you're left with is background gas. So here's your particle. There's a background gas, which is typically, even in a dilution refrigerator, there's a tiny high energy part of your distribution of helium on the walls. And the portion of the helium distribution that's above 4 degrees Kelvin will pop off the wall and go hit your mass, and then stick to your mass. And that leads to a background pressure of about 10 to the minus 16 torr in a dilution refrigerator. You can think of it as a thermal bath, actually. It has a very similar white noise structure to a regular ohmic bath, but it's got a much lower noise value here, 10 to minus 18 meters per second, rather than 10 to minus 12. So there's a tremendous benefit if you can move to a levitated mass rather than a suspended mass. And so we have collaborations with Marcus Aspelmeyer's group in Vienna, who's now doing this with superconducting spheres. And I think this is a very interesting path forward. This gets us to an optimized 10 to minus 16 meters per second, 10 to minus 17 meters per second. So we're only 5 orders of magnitude away, actually 4 orders of magnitude away. And then, as I mentioned, actually, people now are getting 10 to minus 16, even 10 to minus 17 torr. We don't actually know, by the way, the background pressure in dilution refrigerator. These are just upper bounds. It could be substantially lower. And if you combine that with some squeezing, you start to get to the point where one sensor, in principle, can be within a factor of 100 of the SNR for one of these dark matter particles. So now you just need more sensors. So here's more sensors. So the concept here is what we call wind chime. And that is an array of these sensors. And the array is important not just because we need better signal to noise per dark matter particle, but also because we want to see the correlation, as you can see here, of hypothetical dark matter going through, the correlation of the mechanical motion. It's that correlation that allows us to reject backgrounds and allows us to really see we have a dark matter particle and not something else. It's also, we think, a new tool for particle physics in the 21st century, kind of a bubble chamber, but they can be used for other sensing. And we're very excited about this prospect. There's some papers here on the theory side, and there's a large collaboration now called the Wind Chime Project, which is run out of Oak Ridge National Laboratory with collaborators around the world, which you're welcome to email me about and join. We always are welcoming more members who want to think about these challenges. I had a question in the chat. I'm going to take it now if I can. If hypothetical dark matter particles do not interact with photonic matter, then how are these particles affected by temperature? So dark matter will equilibrate or quasi-equilibrate with gravitational gases and backgrounds. And that quasi-equilibrium, so gravity doesn't equilibrate, statement 1. But that quasi-equilibrium you get in capillarization will lead to the dark matter particles to have some temperature. I hope that helps. Okay, so let's talk now about the engineering tools that we're building. And we need a couple of things, right? You need to sort of figure out, first of all, what is your science? Like, how do you define your specifications? What are you trying to measure? What are you trying to bound? That helps you then understand how to segment and integrate your problem. So you want to break your problem up and remember how to bring it back together. This then determines the interfaces and standards that you actually need to make individual components work that then integrate together. You can then do modeling and optimization from this loop in order to make a much better engineered system, which then improves your science. And this is a sort of virtuous cycle of systems engineering that we hope to enable for quantum systems. So an example of doing this is in automating quantum experiments. So this is a picture of Dave Wineland, who won the Nobel Prize nearly a decade ago now for ion trap-based quantum computing, tuning stuff in the laboratory. This is a stage shot. Dave claims that no one lets him in the lab anymore. So, but the point is that there's a huge amount you actually have to do by hand in the lab, and we believe that there's better ways to automate that. So we built a project some years ago to automate the tuning up of silicon-based quantum bits. So these are qubits that are sitting at the surface of a semiconductor or in a two-dimensional electron gas. And you sort of define the qubits by applying electrostatic voltages to gates, which deplete the gas and allow only a narrow set of islands to exist where the electrons will live. There's a variety of ways of doing it, but the thing I want you to think about is the gate problem, which is that you're trying to find this optimum spot where there's just one island per pair of gates. Island here, 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 and nothing else. And in each of these islands, you only want one electron. So this is a huge parameter space. This device is from Jason's group at Princeton. This is a huge parameter space. And you need to be able to put this thing in the fridge and cool it down and get it ready to go do experiments with it quickly. So the question we asked was, can you sort of come up with the root access to this experiment so that you don't have to do all the work? And that project, we actually kind of what we did was we broke it up into building a training data set, doing machine learning on that, building trained networks, and then building a different loop between that network, which was modeled, to a real system and looping that about. And if you want to play around with this, we have a GitHub called QFlow Lite, which has working code and a data set that you can play with. And then since then, we have a QFlow, which is the actual automation system, which has been deployed in Wisconsin at Intel. But the basic idea is that you have this sort of structure. You can simulate tune-up in software. And what you're doing here is you're comparing what the potential across the nanowires, which produces a potential for electrons. And here's a hypothetical electron gas that fills in there. Change that center barrier, you get two islands rather than one. If you look at transport through the system, here you have these sort of straight lines that represent when the leads are aligned with this Fermi surface. And here you have to align this Fermi surface and this Fermi surface with the leads in order to get transport, so you get these triple points. So you're looking for morphology differences in, for example, transport through this device. And so we were able to take this morphology sensing, measuring basically what things look like, with machine learning-based image classifiers, and more recently, ray classifiers, to take this, process it, put it through the networks that we trained on simulated systems, modeled systems, optimize, and then terminate. And this has led to an automated loop with Wisconsin group, which fully tunes the device. We've added now some script-based tuning in order to be able to not just fully tune the device, but also be able to go from you push the button on the fridge to cool it down, you come back the next morning and you have quantum dots. So what we really want to do though, and this is now pivoting to the work at Riverlane, is to make this work broadly. And you really want to build a scalable machine, which is a complex classical quantum system. So this is a picture of Google's machine from 3 years ago when they did the quantum computational supremacy experiment. And you can't see it. The qubits are right where my dot is, right in the center. There's a little chip there. Then there's all of this wiring and low noise amplifiers hanging out in here. This is in turn controlled by a bunch of instrument racks, which are FPGA-based systems here and here. And then that is all orchestrated by a central computing system. So this complex control system was actually what actually runs these experiments and makes your quantum computer work. And the challenge is building this orchestrated system here in a way that makes the best qubit physics come out at the bottom. And as we'll talk about, that enables quantum error correction, which is the key to making these systems actually scale once you take into account the inevitable errors. And I will mention that if you look at like a full stack quantum computing system, you have the qubits down here. I mentioned the amplifiers already. You also have the pulse generators. These are all controlled by essentially FPGA systems. So they're very hardware specific. They're run close to, with the state-of-the-art microwave systems, mostly from the telecommunications industry. And then above that, you have some sort of qubit abstraction layer, which converts all this complicated microwave engineering to do a pi pulse on that qubit, please. So if you go to one of these beautiful commercial interfaces, for example, as provided by like IBM's Qiskit or Cirq or one of the other providers, right? They show you this, they don't show you this. So when we talk about building an operating system for quantum computing, it's talking about making all of this work for multiple qubit types. I will mention that when you do this stuff, there's a bunch of things that happen in between that are also quite important. You need to be able to test everything with, for example, unit tests is a framework that's used in software engineering. That's a very helpful way of looking at how to do this. But there's other engineering tests. And you also need to be very careful about the APIs and the interfaces between the different layers of your stack. So it's a very complicated engineering problem, lots of work to be done. One of the things that we do to make this work efficiently with large teams is to break it up into sort of first a high-level modeling and understanding pass, which you can do on pen and paper or with simple Python code, followed by a framework which produces like reference components and reference models. By the way, PsiQuantum does it this way as well, followed by a kind of a hardware-aware layer. This hardware-aware layer is understanding the limits of your pulse generators, the limits of your amplifiers, the limits of the different interconnects that you have, and incorporating that into your modeling. And then you actually want to take that model and bring it down to implementation on FPGA, field programmable gate array, or if necessary, ASIC, application-specific integrated chip, so custom silicon. And then finally, you take this and bring it to your qubits. You spend the most time, the most exploration up here, and once you've gotten down to here, you basically have your solution and you're implementing it. This is type of pipeline is something that we're working on at Riverlane because that's what you do at a company. You don't just explore, you convert into implementation in a deployed manner, so you can put it into production. And part of the process is also making certain that we have all the tooling that goes alongside. So if you're doing software development, you want to have a debugger, right? Well, this full stack needs a whole bunch of different elements that act as individual level debuggers of the whole system. And that tooling turns out to be something that everyone needs today, even though not everyone needs a scalable quantum computing stack. So let me give you now an example of how we apply this in practice under the context of the main target of our operating system at Riverlane today, which is an error correction operating system. As you may be aware, quantum bits aren't perfect. Part of that is just the nature of the universe, which is that entanglement is ubiquitous. Everything wants to get entangled with everything else, and the challenge is preventing that entanglement, right? Making really good shields and boxes and controlling what gets coupled to what, while still enabling control of those systems so that you can actually measure things. In order to make a quantum memory, which no one has yet done, quantum memory being a quantum state that lives forever. I'd be happy with a year, by the way. Forever's a long time. But the best that has been done is 3 hours. And that was actually with a large number of systems that were really hard to interface with. So I want to see a year. Can we engineer it? Well, what we need first is incredible qubits. So here is some beautiful renditions, artist renditions of qubits. Beautiful Terminator-esque, I guess. And then you need to put on top of these qubits, because even the best qubits aren't good enough, a technique called quantum error correction. In quantum error correction, you take the information in your qubits and you spread it out in entangled states across a large substrate in such a way that if any one of those qubits or some fraction of those qubits get destroyed or their information gets modified, you can detect that modification and correct it. Now, quantum error correction was discovered back in 1996. And in the 25 plus years since then, we've had a lot of continuous improvements in what you can do with it. But the dominant theme for today's error correction in practice is what's called surface codes or planar codes, where you use variations of topological quantum computing ideas in order to store your information. But there's no topological computer here. It's just you have a mathematical structure of your code. And a key feature of this is that, so in this picture here, each of these circles represents a qubit. The white circles are where your quantum data live, and the dark circles are the qubits that you use to extract the error information. Because what you're doing is, in space and in time, you're trying to extract the errors that are happening because your system is being heated by noise, and you're trying to cool it by using zero entropy auxiliary qubits that you then measure and feedback with. That loop has to be done very fast. It has to be done a lot faster than your qubits decoherence time. And so not only do you need these qubits and the math of error correction, you need really great engineering. in order to create a closed loop that solves a hard classical problem, which is decoding this information, at a timescale fast enough to keep up with the qubits. It's actually a lot like a particle physics experiment. You're getting, we're estimating when you go to on the order of 100,000 to 10 million qubits, that's the range you need to make a large-scale computer, that you're looking at around 100 terabytes per second of data coming out of your computer because of all of these syndrome measurements. Like every microsecond, you're measuring half of your qubits. And you have to process that. And you need the decoder to keep up. The faster your decoder can work, the faster your quantum clock speed, because you can't do logical operations till your decoder has solved. And that means that you need decoders that scale. So I will say that it's been a tremendous year this last year for error correction. I'm not going to go into too detail. This is an example from Andreas Walras' group at ETH Zurich. This is a superconducting processor built explicitly to implement that surface code you just saw. The Ds are those white qubits, the data qubits. The X's are syndrome qubits that pick up X information. The Z's are those syndrome qubits that pick up Z information. Each of these little each of the little yellow objects is a superconducting qubit. The links in between, the blue links, are actually the couplers between these qubits. You've literally laid out your error correcting code in physical hardware. This is code design at its best. And the algorithm is simple. You measure the syndromes, repeat it many times, and you decode in totality. They were not able to decode online. They weren't able to make this closed loop, even with only a 3x3 grid. And that's because the decoding problem was actually not easy. It's not exponentially hard, but it's not easy. And here's kind of what the decoding problem looks like. So here are these data qubits and syndrome qubits we mentioned before. So let's say that you have an error here, but you don't see that error. What you see is you see the two syndrome qubits adjacent to it light up. And the decoding is to recognize that these two objects here mean that the error is probably there. Which is simple. And now what about this problem? So I've got this one lit up and this one lit up. Given that errors are rare, so say an average of 1 per 100, what is the most likely error path you have? Well, it's the straight one. The Manhattan distance is minimized. Well, that's good. At this. So now you have a lot of options. A number of things have lit up. What's going to be your best path? Well, it turns out that it's hard to find it generically, but you can work through and figure out that this one is the most probable error to have occurred, even though other errors could have also occurred. So decoding that is the key. The real systems, though, look like this. So solving this problem is like a tough Sudoku puzzle, doable, but you have to have enough time. And so what we're doing at Riverlane is building the combined software and embedded system solution, the decoders and the control systems, in order to do this at speed. And I'm happy to talk more about that offline. But I just want to end here. So when I first pitched the National Quantum Initiative within the administration, this was the slide I used. I said, hey, you know that there are things quantum computers can do that no classical computer can. The most famous of which is probably Shor's algorithm and quantum simulation, which I talked a little bit about. These are the home runs in baseball analogy. But what we're doing today is small ball. We're trying out things here in the infield. And the real question is, how do we get from here out to here? And for me, the answer is this. We need to do error correction. That's actually our path. We need to demonstrate a shift from what's called NISQ, noisy intermediate scale quantum, where I prepare qubits, I do a bunch of coherent operations, and then I measure at the end, to this very measurement-heavy workflow of prepare, coherent measure, coherent measure, coherent measure, coherent measure, coherent measure, to keep our qubits alive, well, for a year. So with that, I will say thank you so much for your time, and I'm happy to take your questions. None. I want to keep a quantum state alive for a year for several different reasons. So first of all, it's a lot easier to keep a quantum state alive than to run a computation, but it's a necessary precomponent. Second of all, there are some very interesting ideas, mostly in the field of quantum gravity, that suggest that there might be fundamental limits to time and space coherence. And the longer you can sustain a quantum state, the more tightly you can constrain these theories. In fact, I have a whole nother talk about the future of quantum gravity on Earth. And actually, one of the ways to try and bound it is by doing these memory experiments for longer periods of time. But I didn't want to get into that so much today because who here is a quantum gravity expert? Okay, who here is a quantum gravity novice? Okay. So anyway, like I said, maybe a different audience. But thank you for that question. So QKD is a technology without a market, which is to say that it is so QKD is definitely something right down here. You notice I labeled quantum networks. So if you can do QKD, then you have a baseline of the right type of fiber, the right type of detectors, the right type of systems to be able to then start to entangle things at distance. And as I tried to say towards the beginning, the sense that I have, and actually is maybe reflected by, for example, this quantum networking report from a year ago, is that the real opportunity in the technology space is the networking of quantum devices, not so much QKD per se. That's true for the US. It's true for areas where public key encryption is embedded in how we do things. There are maybe areas of the world where people don't use public key encryption. So public key encryption, for those who aren't familiar, when you go to make an e-commerce purchase on the web, you're doing public key encryption. You're doing a small sharing, saying, yeah, you're really that company, Jeff's Emporium. And at Jeff's Emporium, we can agree, who's Jeff? What do you mean, who's Jeff? He's the bald guy. Okay, she gets it. Go to Jeff's Emporium, and there's a little link, right? That first link, the fact that you're confirmed that it's Jeff's Emporium, not some other cut-rate site, like Juan's. That story there is really that of public key encryption. And we use that in our e-commerce all over the place. But it's not guaranteed that that's the right solution. It's the one that the US hit upon and now the internet uses. When that's your background, QKD is not very useful. No. It's a bunt, and like just get a single instead. It's a sacrifice fly. I don't know. Thank you for that question. So, I've been working as a scientist for most of my career. I'd only dabbled, as it were, in science leadership before going downtown. I created an institute at the University of Maryland called the Joint Center for Quantum Information and Computer Science, and had experience leading that smaller scale effort. But one of the things about working at OSTP generically, working within the White House generically, and this may sound counterintuitive, you have all the responsibility and none of the power. So the White House doesn't execute anything. The White House directs agencies to do things. So when you're sitting in that role, you have the responsibility to get it right, but you can only lead by consensus. And so recognizing that consensus building is the essence for making this so the US government has like 2 million employees, not including contractors, right? It's like a fifth of the US economy, right? So just recognizing that making that machine move is the art of consensus building, and integrating that in was really interesting. And the other was the power of walking in the hallways And I encourage you to do it also, here, which is there's lots of people around. And I'm certain many of you have gone to a conference, run into your colleague from Illinois and be like, oh yeah, how you doing? Seen you in 6 months. Because you're so insular. So walking the halls to be a great secret weapon for making progress. Because again, you have to build these consensus of future effort. And recognizing that was a big insight for me. Yeah.
You're the right person. I know you don't ever how long NQI will last.
Yeah.
Just for comparison, NNI was about 9 years from 2001 when it started till.
So there are ways to look at indicators for this. And don't tell the NNI that they're not still going. They would be sad to hear that.
They have a website. So.
Yeah, they even have a budget. They have a whole budget outlay. But it has become more diffuse, right? So the question is not so much how long will the NQI live. The answer is infinity. That's all these initiatives. But it's more how long will it be an integrated object that's more than the sum of its parts. So the way I look at this is that the initiatives and enterprises build and maintain momentum dynamically in the political environment. So what that means for the NQI is that you don't rest on your laurels. Say, great, we got the NQI done, let's go do this for 11 years, right? So the CHIPS Act, as an example, is this huge investment made by the Congress and the President into a wide set of technologies. A bunch of it is expansions and integrations of things that were happening under the NQI that are now codified into law. So for example, I created 2 different coordinating bodies for the NQI, one of which was legislated, one of which we knew we needed, but Congress didn't agree. So we created it, we used it, but it could go away at any moment. Through the CHIPS Act and the National Defense Authorization Act, that body became codified in law. So that ability for Congress to come back, for people to recognize that that's important, that's what reinvigorates these things. So the point is, in 2018, it was an 11-year project. The re-up of these ideas, these authorizations, and the inclusion of the changes that have been happening as to now the new legislation for it suggests 11 years from this year. And just keep an eye on how the different elements that comprise NQI are continuing to be supported by future efforts and legislation in order to understand its longevity. I think that we were very careful to put the policy in place before the NQI was passed. And that policy was very clear that it was a science project, which meant there were 0 promises to Congress they would see any technology by 2030. No, if we train lots of people and try lots of things, it is a success. It wouldn't guarantee continuation, that's right, because if you train a lot of people and try a lot of things and none of it works, then maybe it's not in the public interest to spend all that money in the future. There are clear goals, but the clear goals are not build a quantum computer. They're not technology-driven goals.
It's about quantum engineering.
Yeah.
So to build on that, even though it's science, engineering and a good co-creation and feedback loop to achieve.
Right. And the adolescence, yeah. So this is a great question. maybe I will say, answer it quickly in two parts. So the first part is, we're at this birth of quantum engineering, and I think that I'm making this commentary now because in 2024, the NQI is going to do its next plan, right? So the first plan is executing now. I already talked about that. The next plan will come together. We need to be addressing, is it the time to get deeper into engineering? For an engineering school or college, there's this science of engineering. I talked about this loop in systems engineering between the science of engineering and the way you break systems up, the way you bring them back together, the way you test your models, optimization. And that science is really disparate right now. No one can agree on even the specifications for a quantum computer. Like, oh yeah, this one does this many QOPs. No one knows what a QOP is. It's quantum operation per second? Not really, no one agrees. And so, but also things like pulse generator specifications. Like, it works really well for telecom transmission, we know what we want, but we don't have the same equivalent class for quantum pulse generators and quantum amplifiers. And so, understanding each of these little components, building the specifications for how they fail rather than how they succeed, and understanding their modeling and integration is the engineering challenge ahead of us. Whether that's going to happen at a university or an industry, or most likely at some intersection of the two, is a big open question. But I will say that engineering is a practical art, so it's also really about checking that you did this thing and then it actually works somewhere. And this is where a place like Illinois could make a huge impact, because you have people doing really hard stuff and also doing really interesting engineering, and they're right next to each other because you're in the same college. It's a really interesting opportunity there.
Thank you very much, Jake.
Thank you.